Everything so far retrieves once and answers once. One search, one shot. If that single retrieval misses, the answer is wrong, and the system never knows. An agent changes that. Classic retrieval augmented generation operates as a strictly linear control flow. The logic moves in exactly one direction, with no mechanism for mid-course correction. This schematic shows the baseline sequence. It begins by embedding the user query into a vector. Then it executes a single search against the retriever to pull similar text chunks. Immediately after this single pass, the architecture forces the system to generate an answer. This sequence relies on the assumption that the first retrieval will yield perfect evidence. In production, that assumption is a structural vulnerability. That vulnerability collapses when the system encounters a query that is highly vague, contains multiple distinct parts, or demands widely scattered facts. For these complex requests, a single retrieval pass mathematically guarantees that some necessary context will remain hidden in the database. Because the pipeline is hardwired, there is no step where the system can evaluate its own retrieved context before it begins writing. As indicated by the failure point here, if retrieval misses the needed facts, the connection is severed with no path back. The result is a confident answer built on thin evidence. The model generates a response that looks correct, but is fundamentally a hallucination. The solution is not to build a better single search. It is to engineer a system that is capable of searching multiple times on purpose. We solve this by breaking the hardwired pipeline and stopping the forced sequential retrieval process. In this new architecture, retrieval becomes a tool. The search function is exposed directly to the LLM reasoning core, which now decides when and how to call it. The model is no longer a passive data recipient. It is free to decide how many times it searches. It might make 0 calls, a single call, or n parallel calls to gather disparate facts. To navigate this, the model relies on tool metadata, descriptions, and typed arguments to understand the scope and the boundaries of its available resources. This structural transition transforms the system from a passive text generator into an active decision-making reasoning engine. This reasoning engine operates through a specific cognitive cycle, known as the react pattern. The cycle begins with reason, analyzing the goal. This leads to act, where the model executes a specific tool, like a targeted search. Finally, observe, where retrieved outputs feed directly into the next thought step. Each observation informs the very next reasoning step, creating a continuous loop of verification. Interleaving thinking and tool use allows the probabilistic model to verify facts deterministically before it completely commits to a final answer. When you place the react pattern inside an autonomous loop, retrieval becomes entirely dynamic. This is the Agentic RAG loop. It begins by detecting a knowledge gap, specifically asking, "What do I still need to know to answer this?" The agent initiates action by calling the scaled retriever to fill that gap. Once results return, it reads the content and judges its relevance at the decision gate, asking, "Is there enough evidence here?" If the evidence is thin or irrelevant, the agent does not guess. It takes the no path, reformulates the query, narrowing or splitting the task, and retrieves again. This dynamic loop repeats itself iteratively, actively searching and refining its queries on purpose until the necessary facts are strictly secured. Only when the evidence is sufficient does the loop exit to synthesize a grounded final answer. Retrieval has evolved from a static one-way search into a goal-driven reasoning process. This is Agentic RAG. The contrast between these two systems is a matter of resilience. The one-shot pipeline on the left has no recovery path if the search misses. The agentic system on the right recovers from a miss by actively deciding to search again. This dynamic iteration is what protects an enterprise application from presenting confident but false information to its users. This is neuralsca, neurals.ca, visualizing the systems behind modern AI. Transitioning to an agentic architecture is the necessary step for making AI trustworthy in production environments. The agent now has the autonomy to search repeatedly until it finds the truth. But this creates a new challenge. How does an agent know the optimal way to break a complex question into the right series of searches? And what happens when the answer doesn't live in a single passage, but exists only in the invisible relationships between multiple disparate facts? So the agent can search again and again. But two questions decide whether it is smart or just stubborn. How does it break a hard question into the right searches? And what does it search when the answer lives not in any single passage, but in the relationships between facts? That is where planning meets structured knowledge.
A basic pipeline takes a user prompt and retrieves the nearest neighbors in a single pass. An agentic system evaluates the request and calculates the specific sequence of operations required to resolve it. The first capability of an intelligent agent is query decomposition. If a question is multi-layered, the agent must recognize that a single retrieval is insufficient, and instead draft a series of subqueries to gather the necessary context. The second capability is the ability to navigate structured relationships. When an answer is hidden in the links between distinct facts, the agent must know how to move beyond text similarity and traverse a deterministic map of entities. This finale focuses on the final architecture needed to bridge these gaps: the integration of autonomous planning, intermediate validation, and structured knowledge traversal. When a user provides a prompt with multiple temporal and relational constraints, the standard RAG pipeline often shatters. The retriever tries to find one single document chunk that satisfies every condition simultaneously, finds nothing, and returns an empty or irrelevant result. Query decomposition prevents this by inserting a reasoning model to act as a planner. Instead of searching for the full prompt, the planner divides it into ordered, manageable sub-questions. Take a question like, which director's films since 2014 starred the lead from his 2010 hit? The reasoning planner breaks the complex query into 3 logical paths: find the director, their recent films, and the lead actor. Each subquery triggers its own targeted retrieval. The agent searches not for a single magic paragraph, but 3 specific, isolated data points. These results are then linked through sequential chaining. In this architecture, the output of the first search physically becomes the input for the next. We see the flow here. Step 1 identifies director Christopher Nolan. This entity is fed forward into Step 2, searching for films released after 2014. Step 3 identifies the lead actor, synthesizing the definitive answer. Nolan directed Interstellar in 2014, starring Matthew McConaughey. This step-by-step reasoning transforms a flat search into a coordinated sequence of actions, allowing the system to resolve questions that no single document could answer. This reliance on chaining introduces a specific risk: silent error propagation. If the first search retrieves a hallucination, that error is passed into subsequent subqueries. The agent will continue to execute its plan with perfect internal logic, unaware that it is building an answer on a false premise. To stabilize the chain, we must implement intermediate validation steps between each hop. In this validation loop, the agent grades its own retrieval, checking if each chunk is relevant and sufficient to proceed. If insufficient, it enters a replanning phase. It reformulates the subquery and retries the search rather than allowing a weak link to corrupt the output. Implementing these verification gates ensures the reasoning chain remains grounded in factual evidence throughout the entire multi-step process. Even with query composition, there are questions that defeat any purely semantic architecture. Vector databases are built for similarity. They excel at finding passages that are topically related, but they do not map exact deterministic logic. This is an issue when matching specific release years across distinct cast lists and director credits. Semantic search might surface dozens of pages about Christopher Nolan, but cannot reliably draw the exact line through specific years and actors for a multi-hop answer. For these logical intersections, the answer isn't located inside a paragraph of text. It is encoded in the relationships between data points. When the answer relies on a deterministic link between facts, probability-based retrieval is the wrong tool. Production RAG systems are increasingly integrating knowledge graphs and architecture storing exact relationships. Entities like people and movies are nodes. Their connections are edges, typed relationships like directed or acted in, creating a machine-readable map of facts. We do not search this map for similarity. Instead, we traverse it using the language Cypher. This code shows a Cypher traversal. The match syntax visually mirrors the graph structure, defining a precise logical path. The traversal starts at the inception node, following the directed edge backward to identify the specific person responsible for the film. That entity is identified with zero ambiguity as Christopher Nolan.
From the Nolan node, the query follows the edges outward to find his other films, applying a strict filter to return only the movie released in 2014. At the 2014 film node, Interstellar, the system follows the acted-in edges to retrieve the specific cast members. This deterministic path leads directly to the lead actor requested by the prompt, Matthew McConaughey. This path is exact and explainable. Unlike fuzzy vector clusters, the graph provides a complete logical trace of how the answer was found. Modern RAG relies on a hybrid architecture, using vector search for broad semantic recall and the knowledge graph for precise logical facts. Over these 3 episodes, we have mapped the complete evolution of the RAG pipeline. It began with the fundamentals of chunking and embedding unstructured data to make it searchable. We scaled that foundation with ranking and retrieval mechanisms to handle the complexity of enterprise data. And today, we equipped the system with a reasoning engine capable of planning, self-correcting, and navigating structured knowledge. The combination of these layers transforms retrieval from a simple document lookup into a truly autonomous reasoning process. The architecture for production-ready agentic RAG is now complete. The challenge is to apply these layers to your own data.